Okay, so Einstein didn't actually believe these things were real. And now, we've got photos of them. We've heard them collide. We've basically weighed one from 26,000 light-years away. Back in 2019, scientists pointed a planet-sized telescope at a galaxy called M87 and got the first ever picture of a black hole. This glowing, fiery ring wrapped around total darkness. In 2015, a detector called LIGO picked up something even weirder. The sound, basically, of two black holes crashing into each other sent as a ripple through space-time itself. And closer to home, astronomers have been watching a single star whip around the black hole at the center of our own galaxy, close enough to put Einstein's math to the test. Three totally different ways of looking. Same answer every time. Yeah, these things are real. But here's the catch. Nobody actually knows what's happening inside one. So before we get to that mystery, let's start with something simpler. What even is a black hole? Here's the simplest way to put it. A black hole is a spot in space where gravity got so strong that not even light can get out. That's it. That's the whole definition. Einstein laid the groundwork for this back in 1915 when he figured out that gravity isn't really a force pulling things around, it's space and time themselves bending. So imagine cramming a ridiculous amount of matter into a tiny space. At some point, that bending just folds in on itself. And boom, black hole. Now, they're not all the same size. Astronomers basically sort them into 4 buckets. There are stellar mass black holes, a few times up to a few dozen times heavier than our Sun, and those form when a massive star dies and collapses. Then there are supermassive ones, sitting at the center of pretty much every big galaxy, weighing anywhere from 1 million to tens of billions of suns. There's also a rarer in-between category, intermediate mass black holes, and then a 4th type that's still just a theory, primordial black holes which might have formed moments after the Big Bang itself. But here's the wild part. No matter how big or small, black holes are almost embarrassingly simple objects. There's something called the no-hair theorem, and it basically says a black hole can be fully described with just 3 numbers: its mass, its charge, and its spin. And since real black holes don't really carry charge, you're down to 2 numbers. 2. Whatever fell in, a star, a planet, your car keys, none of that history survives. Just mass and spin. That simplicity stops right at the edge, though. Next up, the event horizon, the actual point of no return. The event horizon is basically the black hole's line in the sand. Cross it, and no signal, no light, nothing gets back out to tell the tale. For a non-spinning black hole, it's just a sphere, and its size is set by something called the Schwarzschild radius. The math works out to roughly 3 kilometers for every solar mass. So, yeah, squeeze the entire sun down to about 3 kilometers wide, and congratulations, you've made a black hole. And here's the thing. People get wrong, the horizon isn't a wall. It's not like hitting glass. If you fell through one, especially a big, supermassive one, you genuinely wouldn't feel anything special in the moment. No bump, no signpost. You just wouldn't be able to leave. Deep at the center, though, is something totally different: the singularity. This is where the math just breaks. Density and curvature both shoot up to infinity, and our physics has literally nothing to say about what happens there. Back in 1965, a physicist named Roger Penrose proved that this kind of singularity isn't some weird edge case. It's basically unavoidable once a big enough object starts collapsing. That work eventually won him a Nobel Prize in 2020. And it's worth saying clearly, The horizon and the singularity are not the same thing. The horizon is just a boundary. You can even math your way past the weirdness with different coordinates. The singularity is the real deal, an actual infinity. Now, throw spin into the mix and things get even stranger. A rotating black hole literally drags the fabric of space around with it, creating a region called the ergosphere, where nothing can just sit still. And weirdly, that dragging effect is also a place where you could, in theory, siphon energy right out of the black hole's spin. So, that's the anatomy. Next question, where do these things even come from? For the smaller ones, it's honestly pretty simple. A massive star burns through its fuel, can't hold itself up anymore, and collapses under its own gravity. Straightforward. We get it. Supermassive black holes, total mystery. Here's the problem. We've spotted quasars, powered by billion solar mass black holes from less than 1 billion years after the Big Bang. That's just not supposed to be enough time to grow something that huge. So there are two competing ideas about how it happened. One camp says light seeds. The very first generation of stars collapses into modest black holes, maybe 10 to 100 times the sun's mass. And then those just feed like crazy, way faster than normal, until they balloon up. The other camp says heavy seeds. Skip the star phase entirely. A massive gas cloud just collapses directly into a black hole, instantly giving you a seed of 10,000 to 1 million solar masses. Basically a head start instead of a slow grind. And in 2025, an astronomer named Peter van Dokkum and his team found something that might actually back up that second idea, a weird object nicknamed the Infinity Galaxy, where a black hole seems to be forming right there, in a dense cloud of gas, squeezed between two colliding galaxies. Either way it happens, once a black hole exists, it doesn't just sit there quietly. So, how does it actually feed? Here's something people don't expect. Stuff falling into a black hole almost never falls straight in. Because it's got angular momentum, it ends up spiraling around in what's called an accretion disk instead. And all that friction and turbulence turns gravitational energy into insane amounts of heat and light. And I mean insane. A normal accretion disk can turn at least 10% of the matter falling in into pure radiated energy. Around a fast-spinning black hole, that number jumps to around 32%, and in the extreme theoretical limit, it can push past 40%. Compare that to a star doing nuclear fusion, which only manages about 0.7% efficiency. So, yeah, accreting black holes are basically the most efficient power plants in the entire universe. Though when they're not feeding much, which is the case for both Sagittarius A and M87 right now, the disk gets puffier, hotter, and way less efficient at actually radiating that energy away. Some of that energy doesn't stay put either. It shoots out as relativistic jets, tight beams of plasma blasting out along the black hole's spin axis at nearly the speed of light, sometimes stretching millions of light years. The leading explanation is something called the Blandford-Zernajek process, first proposed back in 1977. Basically, magnetic field lines anchored to the spinning black hole tap directly into its rotational energy and fling plasma outward like a slingshot. And the Event Horizon Telescope's observations of M87 line up with pretty much everything this theory predicts. In 2025, a research group led by Luciano Redzolla ran some early simulations suggesting there might be a second ingredient at play too, something called magnetic reconnection. working alongside Blandford's Najek. And here's a fun detail. M87's jet appears to move at 4 to 6 times the speed of light. Don't worry, nothing's actually breaking physics. It's an optical illusion that happens when plasma is barreling almost straight at us. None of this stays local, by the way. This is called AGN feedback, and it comes in 2 flavors: powerful radiative winds that blow gas clean out of a galaxy and shut down star formation, or jet-driven kinetic feedback like M87's jet, which is dumping an absurd amount of energy, somewhere around 10 to the 43rd or 44th power ergs per second, into its surroundings and literally reshaping the galaxy around it. So get close enough to this engine and things get seriously weird. Even time itself starts to bend. Near a black hole, time genuinely slows down. That's not a metaphor. General relativity says clocks tick slower the deeper you sit in a gravitational field, and right near the event horizon, that effect goes into overdrive. From far away, watching something fall in, it looks like it just freezes, its light stretching out and fading into nothing. And this isn't just theory. In 2018, an instrument called Gravity tracked a star named S2 as it swooped in close to Sagittarius A, hitting about 2.5% of the speed of light at its closest point. Researchers picked up a combined redshift and Doppler signal of roughly 200 kilometers per second, and it matched Einstein's predictions exactly, ruling out simple, old-school Newtonian gravity. Get even closer, and gravity stops playing nice. Stephen Hawking actually coined a term for this: spaghettification. Basically, since gravity gets weaker with distance, the side of you closest to the black hole gets yanked way harder than the far side, so you get stretched out into a long, thin noodle. How brutal this is depends entirely on the black hole's size. A small one will spaghettify you long before you even reach the horizon. A supermassive one is actually gentle enough that you might not notice right away. And this isn't hypothetical either. In 2019, astronomers caught it happening in real time. An event called AT2019QIZ was a star about the size of our Sun getting torn apart by a black hole roughly 1 million times heavier, 215 million light-years away. Spaghettification, live on camera. These aren't just isolated weird events. Combined with the imaging and the orbit data, they're all pointing at the same conclusion. Black holes are real, and we can prove it. So here's the actual case for black holes. 3 completely independent lines of evidence, all agreeing with each other. First up, we've literally taken their picture. In 2019, the Event Horizon Telescope dropped the first ever image of a black hole, a bright ring around M87, just 42 micro-arc seconds across, which works out to a mass of 6.5 billion suns sitting 16.8 million parsecs away. In 2022, they did it again with Sagittarius A, our own galaxy's black hole, a ring 51.8 micro-arc seconds wide, matching a mass of about 4 million suns. Funny enough, even though Esgar A is over 1,000 times lighter than M87, the 2 rings look almost the same size in our sky, because Esgar A is also way, way closer to us. And both images line up with Einstein's predictions for a spinning black hole to within just a few percent. Second, gravitational waves. Back in September 2015, LIGO made history, picking up the first ever direct detection of gravitational waves, space-time literally rippling from 2 black holes smashing together, leaving behind a roughly 62 solar mass remnant. That discovery snagged a Nobel Prize in 2017. And the catalogue's only gotten bigger since, take GW2 31123, detected in November 2023. A 225 solar mass remnant born from two black holes weighing in around 137 and 103 solar masses, the heaviest merger we've ever caught. As of the most recent catalogue, released in May 2026, the LIGO Virgo Kagra network has now logged 390 confirmed gravitational wave events, and third, we've literally watched a star's orbit bend to prove it. Beyond that redshift we mentioned earlier, the gravity team pulled off another huge test in 2020, catching something called Schwarzschild precession, where S2's orbit around Sagittarius A slowly rotates over time, exactly like general relativity says it should. When they crunched the numbers, the ratio of what they observed to what was predicted came out to 1.1. Basically a perfect match. Pictures, sound waves, and orbiting stars. Three totally different tools, and they all say the same thing. But here's the catch. All of this evidence only tells us what's happening outside the horizon, what's going on inside. Still a total black box. Turns out black holes aren't just gravitational monsters, they're also thermodynamic objects, which is a pretty weird sentence to say out loud. Building on some earlier work by Hawking, a physicist named Jacob Bekenstein proposed back in the early 1970s that a black hole actually has entropy, and it's tied directly to the size of its horizon. Then, in 1974, Hawking took it further, showing that quantum effects right at the edge of a black hole should cause it to slowly leak out thermal radiation. Problem is, for a black hole the mass of our Sun, that process would take about 10 to the 67th power years. So, yeah, nobody's ever actually detected this Hawking radiation directly. It's just too faint. And that raises a genuinely uncomfortable question. If a black hole eventually evaporates away completely, what happens to all the information about everything that ever fell in? This is the black hole information paradox, and as of 2025, it's officially hit the 50-year mark, still totally unsolved. Then there's a newer headache, courtesy of the James Webb Space Telescope. JWST kept finding supermassive black holes and these strange objects nicknamed little red dots that looked way too big for how early they showed up in cosmic history. It seemed to break our whole picture of how these things grow. But here's the twist. Research published in Nature in 2026 walked that back a bit, showing the actual masses were about 100 times smaller than first thought, more like 100,000 to 10 million suns instead, which takes a lot of the pressure off that impossible black holes panic. So, what's next? A next-generation Event Horizon telescope is coming, promising even sharper images. LISA, a gravitational wave detector in space, is set to launch sometime in the 2030s and should catch supermassive black holes merging across cosmic history, and pulsar timing arrays are already picking up a constant, low hum of black hole mergers happening throughout the universe all the time. So, here's where we land. The outside of a black hole, pretty well understood these days. The inside, still one of the last great mysteries in all of physics. And that pretty much brings us to the end of the video. If you enjoyed this one, go ahead and hit that like button. Let me know your thoughts down in the comments. I really want to hear them. And if you're into videos like this, do subscribe so you don't miss what's coming next.